Hey, it's a new chapter! We are still doing trig functions, but now we are going to graph, sine, and cosine functions. So if you haven't done this yet with your graphing calculator just because you're interested, well, here we go. So I can identify key features of the graphs of sine and cosine functions. So the example they use is a pendulum as it swings back and forth, back and forth. And if you imagine if you put like maybe a little laser beam on there, and then you just had like a piece of paper going by at a given speed, you would get kind of a back and forth kind of shape. So when it comes to sine, cosine, and tangent, the whole point of learning all these trig functions is because this relationship happens over and over and over and over again. So if you're in my chemistry class, we've seen it before when we're talking about like frequency. I know electricity and sound travel, anything that travels in waves. So if you're talking about like energy or any kind of energy that flows through the air or something like that, you're going to run into these trig functions because their graphs are so good about showing some of this back and forth motion. So without further ado, let's just jump right in. Basic sine and cosine function. So remember in the last chapter, we were using this unit circle, and if we were to look at the values as it goes around, so like let's say, so our x is cosine of theta, our y is sine of theta. So let's look at our x, just our x value. Cosine of 0 would be 1. Actually, I'm going to switch that. Let's start with sine. So sine of 0 is 0, because this little value right there is 0. But then as it approaches up here, when it hits 90 degrees or pi over 2, sine of theta is 1. And then as it goes back down here, it's going back to 0. So you're going to get this wave pattern going back and forth, right? So the book really wanted to have you think about that analytically for a long time before they just show you what the graph looks like. I'm not going to do that. There's a better graph of it later on, but this is generally what our sine function looks like. So notice how sine of 0 is 0, and then as we approach that pi over 2, we go up to 1, and then as we go over to pi, we go back to 0, and then we just go back and forth. Same thing as you go along negative side. So this is what makes sine and cosine such a powerful function, because it can help illustrate this back and forth wave type of emotion. So motion. So here's a table that you can do yourself if you so desired. But you've got f of theta and you've got theta, and this is our sine function right here. And so again, we've got 0, pi over 6, pi over 2, 5 pi over 6, pi. So you can start to see that relationship there. So look at the unit circle and the values on the table. What appears to be the domain? Those domain and range are never going to go away, so get used to it. So remember, the domain is for all values of x. Is there a function? Or is there a value for it? So you can also think about this as maybe like the vertical line test. So for which values of x will the vertical line test cross f of x? In this case, the sine wave goes on forever, so the domain is going to be all real numbers. Same thing for the cosine. Now the range, you could think of this as the horizontal test. So for what values of y can you place a horizontal line that will cross your function? So in this situation, our sine wave never gets above 1 and never gets below -1. So if we make a line up here, it's never going to cross our sine function. So our range is -1 to 1. So let's see here, select all values that are x-intercepts. Now this is not even all the values because they go on forever, but so let's see here, 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi. Are you catching on to the pattern yet? What is the y-intercept? So this one is not an ever-going pattern, but for sine it is going to be 0. This is our parent function. So not this not this module or section, but the next section. If I'm using the terms parent function, we're probably going to start messing with it. So how can you use the unit circle, the table, and your knowledge of coterminal angles to describe the values over the domain? 2 pi over the domain, 2 pi to theta to 4 pi, and over the domain, -2 pi to theta to 0. So -2 pi to 0, and then 2 pi to 4 pi. The values from 2 pi to theta to 4 pi and -pi to 0 will repeat the values. I think that one's it. So yeah, so you're going to repeat ever so often. So the graph shows sine of theta from -2 pi to 4 pi. Use the graph to identify the domain, range, maximum, minimum, intercepts, blah, 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 blah. So here's their much better version than mine. See, they waited till you got all the way down here to show it to you, but I wanted to kind of start that off. So this is your sine function. So let's see here, our domain, again, all real numbers. This is our vertical line test. We can put a vertical line anywhere we want, and it will work. Our range is again going to be -1 to 1. Think of our horizontal line test. Where's that going to work? Where is that not going to work? Our maxima, so the highest that it gets is this number right there. That's going to be, let's see here, pi over 2 plus or minus 2 pi n 1. And then our minimum, what was that, 3 pi over 2. So notice how they're saying plus or minus 2 pi n. So that n is any integer that you want to put in there. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's just showing that it's going back and forth over and over and over again. So the function is increasing, not to be confused with positive, but increasing when it is going up on -2 pi to 2 pi. Oh, wait. Function is increasing -pi over 2 to pi over 2. I apologize, I said that wrong. And then the function is decreasing from pi over 2 to 3 pi. Pi over 2 to 3 pi. And then again, and again, and again, and again. Function values oscillate between 1 and -1 as they increase or decrease without bound. The function is even. So remember, odd functions kind of go up like this. I think it's even. Man, I don't know. Let's check it. Oh, no. Try again. Is odd. Okay, yeah, the function is odd. So here we're going to go through the same steps, except this time we're using cosine. So as we can kind of rationalize through, analytically think about it through, so if we look at our unit circle, cosine of 0 is going to be 1. Cosine of 90 degrees, or pi over 2, is going to be 0. So it's going to be very similar to the sine wave, just moved over a little bit. So it appears the domain of cosine of theta is, again, it's going to be all real numbers. The range is going to be just like our sine function. So I'm trying to breeze through these as much as I can. Select all the values that are x-intercepts. So let's see here. When I'm just going to go down here and look at their graph. X-intercepts negative 2 pi, or pi over 2, negative pi over 2, pi over 2. And then I think that one. And the y-intercept is going to be at 1. The values from 2 pi to 4 pi will repeat, just like our sine function. Very, very similar to our sine function. So here we've got our graph. And again, our domain, our vertical line test, we can do any value of x. Kind of going through all the same stuff again. Our range, negative 1 to 1, our horizontal line test. Our maxima, 0 plus or minus 2 pi. So like 0, 2 pi, 4 pi. Our minimum, or minima, is pi plus or minus 2 pi. And that is at negative 1. So the function is increasing on, where do they want us to start? Pi to 2 pi. Function is decreasing from 0 to pi. Again, it's going down from 0 to pi. It's going up from pi to 2 pi. Function values oscillate, increase, and the function is going to be odd, just like our sine function. Maybe not, just kidding. Clearly, I need to look at our definitions of even and odd when it comes to sine functions. So we've got our parent functions. Now let's see what happens when we start changing them. So it says, I know it got small, I don't know why, but graph f of x equals a sine of 1 over bx, or g of x equals a cosine of 1 over bx. So we are going to start adding stuff to our functions. So in order to kind of talk about some of that stuff, it is useful to understand or to have some terminology, and hopefully some of this is review, maybe if you're in chemistry or something like that. But anyway, these are called periodic functions, as you can imagine, because their values repeat periodically over a given length. And so the length of this interval is called the function's period. So that would be like your sine function from 0 to 2 pi would be a period, or something like that. And you can change that given the whatever situation is. So the graph sine wave functions are shaped like waves. I drew one right there because that's totally such a great whatever. So we've got things like our crests, and then we'll talk about these things down here, kind of like our troughs. These are not official words yet, so it's just kind of the words that we're using. And then what is an official word, boop, is your midline. Typically, especially at this stage of the game, your midline is going to be the x-axis. However, it doesn't necessarily have to be the midline, but that's where we're at. So the midline, in most cases, for your situation now, is going to be the x-axis. The distance that the crest rises above the midline, or the distance that the trough falls below the midline, is called the graph's amplitude. So let's stick with red. So we're going to get rid of crest and trough and say this part is our amplitude. That's something you should know. And spell right. I don't care about spelling. So the amplitude is going to be the same whether you're going up or you're going down. Because remember, if you think about our sine wave or our cosine wave, the top was 1, the bottom was -1. So that is called our amplitude. So the period I had mentioned earlier is how long it takes for it to repeat itself. So because they repeat their values over regular intervals. So in my case up here, we'll do the period in black. So that part is going to be the period. So notice how that's when the whole graph repeats itself. Period. Aren't you guys jealous of my handwriting? So the two things you got to remember here is the period and the amplitude and what they mean. Because that is what we're going to then use to either graph the function or write an equation of the function. So what are the period and amplitude of the basic sine and cosine graphs shown in the previous tasks? So the period is 2 pi. So typically it goes from 0 to 2 pi. And then our amplitude is 1. Yay. Which type of transformation do you think will affect the period of a sine and cosine graph? So if you think about the period, and this is where, like, if you had a slinky, so if you pulled that slinky out, you would be stretching the period. And you'd be stretching it horizontally. So that would probably be a horizontal stretch and compression. Which type of transformation do you think would affect the amplitude? Would that be a vertical stretch or compression? I agree. So the graphs f of x equals -4 sine 2x and g of x equals 2/3 cosine of -x over 4 are shown. What are the period and amplitude of each graph? So the period of f of x, so in spite of the fact there's a 2x in here, remember, sine of any theta can only be from -1 to 1. But then we've got this -4 on the outside. So that is going to change the amplitude. So I'm going to say 4 for that one. Oh, I'm sorry, no. So the amplitude would be our 4. My apologies. The period would be as we're shifting it horizontally. So inside of here, as we start playing with that theta, is going to change how fast or slow we're going up or down. So the period would be pi. Man, I don't know. We'll have to find out. So the period on this next one, let's see here, so if I said it was pi there, I would assume it'd be 1/4 over here. Or no, I'm going to say it's 2 up here. I'm going to say it's 1/4 down here. And then the amplitude, yeah, I didn't think I was going to get those right. So I like visuals a lot more. So here we've got -4 sine of 2x. So again, our amplitude is this outside number. And the way I remember that is sine, no matter what's in the inside here, still only goes from -1 to 1. So like, if we zoomed in here, we could say that part right there just goes from -1 to 1. And then if you think about like that 1 is that peak and that -1 is that bottom, that's only going to get more if we have a number out here. So that's going to be our amplitude. So this 2x, that's probably the one where I'm a little bit weaker on. So let's figure out what's going on here. So our normal graph goes from 0 to 2 pi. This graph shrinks by half. So that actually makes sense if you think about it, because if we look at the inside of this theta here, so whatever that equals is what is going to change our sign or whatever. And so if that x, well, with that 2 out there, it's going to hit 2 pi faster, or sine is going to hit, or it's going to repeat itself faster, so it's going to get smaller. So that's kind of the opposite of what I was kind of thinking, but once I see it, once I think through it, I think it makes a lot more sense. So here, same thing, our amplitude is on the outside, so 2/3. That's what this decimal point is there for. I don't know why they switched to decimals, but whatever. And then our cosine of -x/4. So our cosine is going to get back to our 1 in this case, or 2/3, a lot slower because it has a 1/4 on the inside. So then that means that it's stretched. So then, of course, there's all these negative signs that we're going to have to deal with as well. But they can get kind of confusing because if you flip it over the x and y axis, sometimes it changes, sometimes it doesn't. So let's go into that, shall we? How do the period and amplitude appear to be related to the variables a and b? So the amplitude is a. Our period is, so they're saying 1/b. So I'm going to say 2 pi times b because it's on the bottom there, which you kind of have to think all the way through, but whatever. All right, so here's where they're going to actually like tell us, give us our specific equations that we might be using. So again, create f of x equals a sine of 1/b over x, or g of x equals a cosine of 1/b from a graph. So again, this is our super useful graphic that I would say. So we've got our midline, remember we've got our amplitude, and we've got our period. So for both of these functions, our amplitude is the absolute value of a, and our period is 2 pi times b. And remember, it's 1/b. So keep that in mind. So this is probably a pretty important half of this lesson right here. So remember this. So it says, given the graph of a trigonometric function, you can write its equation by using its key characteristics. So first you need to identify the parent function, is this a reflection of y equals sine x or y equals cosine x across the x-axis? Why are we reflecting it? We're not reflecting it. But we need to figure out what our parent function is. I'm just going to say no. That's a weird question. So a reflection across the x-axis would affect the value of a. It would turn negative. Okay. I don't know why we're starting with that. As I was saying, you need to first identify the parent function. So compare the y-intercept of the graph to the y-intercept of the graphs of sine and cosine. If no horizontal translation was performed, then the parent function is y equals sine of x. And the way they knew that is, so it goes through 0, 0. So which one, sine or cosine, is 0 at theta equals 0. So if you think about our unit circle, when that little guy right there hits 0, that would be our sine, is our opposite over hypotenuse. So our sine function goes through the origin here. So our parent function is a sine wave. So then we identify the amplitude. So our sine normally goes up to 1, but in this case it's only going up to 1/2. So our A, our absolute value of A equals 1/2. So that's our amplitude. And then I assume, are we going to identify the period? So the period, so it starts going up here. When is the next time it goes up? Is 4 pi. What letter? B is what they're using. So our B is equal to 4 pi. I might have written that wrong here. So just, yeah, that's kind of where I thought I was. I'm looking right here, by the way. So our normal period is 2 pi, and then we're multiplying it by b, absolute value of b, and that's going to equal 4 pi. Oh my gosh, I can't write. So then we're just going to do some algebra, right? Divide both sides by 2 pi. Oh, look, the pi's cancel out. So our b is 2. Whoops, eraser. So should you use 2 or -2 as the value of b? You should use +2 because it's an absolute value, and then the sign or the function will take care of the negative. So write the equation. We've got our a, 1/2 sine of 1 over b times x. So there we go. How can you use the values of a and b to write the equation of the graph? It's what we just did. Some of these questions, man, I'm telling you. Now, at least, let's do a real-world example. Create models with sine and cosine functions. So they're using a pitchfork as an example. So a pitchfork, it's kind of this little metal gadget. You tap it, and it vibrates at a certain frequency, and it gives you a certain pitch. And then musicians can then tune their instruments to a given pitch, and they can all be in tune, and they sound much better that way. So sine and cosine functions are useful for modeling, blah, blah, blah. So each sound has a frequency. Notice right there, frequency equals 1 over period, which is the number of cycles completed in a given unit of time. The standard measure of frequency is hertz, which is equivalent to 1 cycle per second. Tuning fork is blah, blah, blah. We've already talked about it. The fluctuation has a maximum that is related to the sound wave's amplitude. That change in air pressure is typically measured in pascals. For each sound wave, determine the frequency Write an equation to model the air pressure P in pascals as a function of time T in seconds, and graph the function. So use a sine function to model a sound wave with a period of that number seconds and an amplitude of 3 pascals. So first of all, we want to find the frequency. Remember, our frequency is, I'm going to write it down, equals 1 over period. So our frequency here is just going to be 1 divided by 0.0025. So our frequency is 1 divided by 0.0025. So here we are. So we're going to write the equation. Remember, we've got an amplitude of 3 pascals. We were told to use a sine function. So that's at least f of x equals our amplitude, 3 sine of some theta. So that's the only one that we got to kind of think about. So it's going to be sine of 2 pi over our, not our frequency, our period. So remember, they gave us the period, and then instead of x, we're going to be using t. So we've got our 2 pi divided by 0.0025 times t. And then, you shove all that in your calculator, and you get this. So once you're here to graph the function, again, you can already figure some stuff out. And when you're drawing these graphs, kind of think about your x scale, because it might make things easier. So we know our amplitude is 3. So when we're drawing this, this is going to be 3. This is going to be negative 3. Sine is going to go through the origin. And then our period is going to be 800 pi. So we could say this is 800. What is half of that? It's going to be 400 pi. And so then we're going to have, actually we need quarters. So it's going to come up, come down, go here, and then back up. Whee! Something like that. I'm sure they did a much better job. Ooh, I lied. So remember, our period is 1 over b. I just took it as 800 when I should have figured out that our b is 1 over 800. My mistake. Don't be like Miss Lynn. Don't make mistakes like that. So remember, our b is 1 over b, and so then when you do the same process I went through, you're just going to get dramatically smaller numbers as opposed to the 800, 400 that I was talking about. So my apologies. So let's do it again. Except this time, the problem is going to tell us to use a cosine function to model a sound wave with a period of 0.005 seconds and an amplitude of 2 pascals. So identify the frequency. Again, our frequency is 1 over the period, which is 200 hertz. That can tell you what note that it's playing. So then when we want to graph it, let's see here. It's given us an amplitude of 2. So we have cosine. We have 2 out here in front. And our period is 0.005. So let's see here. Is that 1 over b? I'm going to get this confused. Yeah. So our b is 0.005. So then we're going to have 2 pi over 0.005, which when we simplify that is going to hit something like this. But again, remember our b is still 0.005, not 400 like I tried to do the last time. So when we graph it, we know our amplitude is 2. Cosine starts up here, and we need our full amplitude, our full period, which is 0.005. So that will be here. And then half of that is 0.0025. And so, and then we need quarters. So and again, we got something like that. So 0.05. So yeah, I think we got the same graph. They're just a lot better at it than I am. Imagine that. So again, our amplitude is 2, -2, and our period is 0. So this is 4, and that's 6. This is hard to see. Figure out which one. I think this is 0.2. And then 1, 2, 3 is 4. And 1, 2, 3 is 6. So 5, I think, would be right here, directly in between 4 and 6. So there you go. The period is affected by the value of b. The frequency is a reciprocal of the period. The coefficient of t in the equation is the product of the coefficient of t in the equation is the product of the what? The amplitude is in the outside, yeah. So the amplitude is in the outside of the functions. That's that number right there. So it was 1 over b, and which I guess is the same as the frequency. So that's why I was getting confused. But so how do you use the period and amplitude to graph each function? So that's kind of what we were doing. You use the period to determine the horizontal distance of each curve, and you use the amplitude to determine the vertical position of the maximum and minimum. You did it. And I think that's it for this lesson. Try out the Check on Learning and see how it goes.